Let's look at an example involving power. You'd have a 30 kilogram box that you are going to push up a ramp, a length of 5 meters, and we want to know if you push the box up the ramp in 4 seconds, what is your power output? And we're going to assume the ramp is frictionless, but of course there is gravity, so it does require effort for you to push this box up the ramp. So we want to figure out power. Well, the power output of U will be related to the work you do divided by the time it takes you to do that work. We know the time it takes is 4 seconds, but we don't know the value for how much work you do, so we'll turn to our conservation of energy equation to figure out work. Start by defining our initial and final moments. The initial moment, the box is at rest at a height of 0. That's the moment shown in the drawing. At the final moment, the box will be at the top of the ramp, which would be a height of 5 meters times sine 30 degrees. And it will be moving at some speed v. So you're going to push this box up the ramp. The entire time you're pushing. And so when it gets to the top of the ramp, it will be moving some speed. I don't know what that speed is just yet. Let's define our system to be the box plus the Earth. The box is changing height, so I'll include Earth in the system so we can talk about gravitational potential energy. Are there any external forces that do work? Yes. Your pushing force will do work on the system. So I am not part of the system. I am the one exerting this force, so that is an external force. I push along the ramp. The displacement is along the ramp, so that force will definitely do work. In fact, it will do positive work. We're ready now to plug values into our conservation of energy equation. Initial kinetic energy is 0, nothing is moving. Initial gravitational potential energy is 0 because the box is at the bottom of the ramp. Elastic potential energy is 0 because there are no springs anywhere. I'm going to do work on the box as I push it up the ramp. I will try to figure out the value of that work. The final kinetic energy will be 1/2 mass times speed squared. I don't yet know the speed when the box reaches the top of the ramp. The final gravitational potential energy will be mgh with the height of the ramp. And the final elastic potential energy is 0 because there are no springs anywhere. So all that is left now is to find a value for the speed when the box gets to the top of the ramp. If I know that, I can find a value for work and plug that value for work in to find power. So let's find the final velocity or the final speed. For that, we can go back to kinematics. So we know that displacement equals initial velocity times change in time plus 1/2 acceleration times change in time squared. Well, the displacement of the box will be 5 meters. That's the distance it travels along the ramp. The initial velocity is 0, so we get 5 meters equals 1/2 acceleration times the 4 seconds it takes to push the box up the ramp squared. That gives us a value for acceleration. Initial velocity is 0, so the final velocity is our acceleration times the 4 seconds that the box accelerates for, giving us a final speed of 2.5 meters per second that we can plug in back into our conservation of energy equation. Doing that, we solve for work and find that you do 828 joules of work pushing the box up this ramp. To find power, we do 828 joules divided by 4 seconds. Comes out to just a little bit over 200 joules per second. A joule per second is the same thing as a watt, so we could also say that your power output is 207 watts.